And so we want to consider component vectors. You see, component vectors are those vectors you represent like this, having I and J and maybe K. If it's having I and J alone, it is two-dimensional. If it's having I, J, and K, maybe minus 3K, it is three-dimensional. And so let's assume we have a vector A now. Vector A, making an angle of theta to the horizontal. You see, we can resolve these vectors into components. If you resolve horizontally, we have AX, which is A cos theta. So AX is the horizontal component, and AY is the vertical component. Now, mind you, we are just dealing with vectors in two-dimensional Cartesian coordinates. You see, vector A can be written as AXI plus AYJ. Now, representing this vector like this is to represent it in component, but mind you, just in two dimensions because it has just I and J. One of the things we can talk about here is the magnitude of the vector. Magnitude of component vector in two dimensions. You see, the magnitude of component vector in two dimensions is given as AX square plus AY square all into square root. This is symbol for magnitude. Magnitude. So I call this magnitude of vector A. Vector A. And it's given as this. So this is how you find the magnitude of a vector. And that thing we want to talk about here, or we could talk about here, is the unit vector. Now, the unit vector is a vector whose magnitude is 1, or you say unity, and it is given as, that unit vector is given as. So if I'm talking about unit vector of A, now it's given as the ratio of the vector A over its magnitude. So you can say that unit vector is the ratio of a vector to its magnitude. Remember, this is symbol for magnitude. And how do we represent vector A? We say vector A can be represented as this, Abi. So you can replace this with AXI plus AYJ all over its magnitude. So this is the unit vector. Either you get it like this or like this. That's unit vector. And if you find the magnitude of this vector, you will get 1. That's why it is called a unit vector. We'll come to take that as we take example, actually. I will explain this. Lastly is the angle of a vector. The angle of a component vector. This is the angle a component vector makes with the horizontal. And it is given as theta, which is equal to tan inverse of the vertical component over the horizontal component. Now to get our theta, the vertical component over the horizontal component. So that's that about vectors in two dimensions. Let's just take an example under this. Example 1, given that vector C is equal to 3i plus 4j, find its magnitude, the unit vector of C, and then its angle. Now, to solve this question, we are given that vector C is given as 3i plus 4j. And so number 1, let's find the magnitude. So magnitude of C should be given as 3 squared plus 4 square all into square root. And this will give us 5 as the answer. Now next is the unit vector. What then is the unit vector? The unit vector of C, this is how we represent unit vector. This is symbol mu. Unit vector of C is simply equal to vector by its magnitude. So what's vector C? 3i plus 4j over the magnitude, that's 5. You can take it like this, it can be expressed like this. 3 over 5i plus 4 over 5j. Or you can further break it down. This will give us 0.6i plus 0.8j. That's that about that. Now, you see, if you find the magnitude of this, you will get 1. Meaning that if you want to find the magnitude of this unit vector C is going to be 0.6 square plus 0.8 square all into square root. And that will just give you 1. That's why it is called unit vector, because the magnitude of that unit vector should give you 1. That's that about that actually. We're not asked to get that. Lastly is the angle. The angle of vector C is given as tan inverse of the vertical component, which is 4, over the horizontal component, which is 3. This will give us 53.13 degrees. Vectors in 3-dimensional Cartesian coordinates. This is like the edge of a box. You know, a box will look somewhat like this, and then draw like this, and then it goes like this, and then like this. Somewhat like this. Don't mind my diagram though, but yeah. And then goes like this, and then somewhat like this. You know, my point is, looking at this is like your Y, your X, and your Z. I know each of those plane here and here make 90 degrees. This and this make 90 degrees, and this makes 90 degrees as well. And that's what we can see here. Let's say we have a vector now, a vector that protrudes out of here. Now, let's say this vector A makes an angle of theta to the horizontal, theta x to the horizontal, and an angle of theta z to the z axis, and then an angle of theta y to the y axis or to the vertical. Okay, now this vector A, well, we've said so many things about what we can find about component vectors actually. If you want to get the magnitude of vector A, or this vector A can be represented as AXI plus AYJ plus AZK. That's to represent this vector. And this AX is given as A cos theta x. And AY is given as A cos theta y. And AZ as well is given as A cos theta z. So you use cos for each of them, unlike where we use sine and cos for the 2-dimensional Cartesian coordinates component vector. Here we use cos. But cos of the angle is made with x, cos of angle is made with y, and cos of angle is made with the z. Now, again, is to get the magnitude of this vector. Magnitude of this vector can be given as ax squared plus ay squared plus az squared all into square root. I didn't go about defining the magnitude of the vector or talking about much about it because we said it in the 2-dimensional case. Again, is to get the unit vector here, C follows the same pattern. Is the vector over the magnitude. So say vector A over the magnitude. So in this case, it's going to be AXI plus AYJ plus AZ. Okay, all into magnitude of A. Don't have to do that in this case. And lastly, to get the angles, you see, the angle of the vectors, here you get 3 different angles. To get theta x, it's simply going to be cos inverse of AX over magnitude of A. And to get theta y, is going to be cos inverse of AY over magnitude of A. And to get theta z, is going to be cos inverse of AZ over magnitude of A. So that's how to do this for 3-dimensional Cartesian coordinates. We'll take one example under this now. Okay, example 2. Given that vector D is equal to 3i minus 2j plus 5k, we have to find the vector, the magnitude of D and the unit vector of D. To solve this, all we just need to do is to say that magnitude of D is given as 3 square plus minus 2 square plus 5 square, all into square root. And this will give us 6.16. That is the magnitude of D. Now, to get the unit vector of D, that's the second one. Unit vector of D is given as the vector by its magnitude. That will be 3i minus 2j plus 5k all over 6.16. You can further express this as 3 over 6.16i minus 2 over 6.16j plus 5 over 6.16k. So that's how to get the unit vector in 3 dimensions. We can also get what we call the directional cosine. The directional cosine, or just the angle it makes to the x, y, and z. Obviously, we've said that before. Theta x should be cos inverse of 3, its value in the x, over the magnitude, 6.16. I'll get what this should be. Theta y is just the cos inverse of minus 2 over 6.16. And we get what that should be. And then theta z is cos inverse of 5 over 6.16. And you get what that should be. Addition and subtraction of component vectors. Let's take example 1 now. If vector B is given as 3i plus 6j plus 7k, and vector C is given as minus 2i plus 3j minus 2k, find 1, b plus c, 2, b minus c, and 3, 2b plus 3c. Let's take the first one now. The first one says b plus c. And that would be b is 3i plus 6j plus 7k added to minus 2i plus 3j minus 2k. So this is going to be 3i plus 6j plus 7k plus times minus, that's minus 2i plus 3j and minus 2k. Then we add the process of addition of complement is just to add the i to the i, the j to the j, and the k to the k. So this is going to be 3i minus 2i. That will give me 1i. This is 1i. Now 6j plus 3j will give me 9j plus 9j. And then 7k minus 2k is going to give me plus 5k. So that's the b plus c. Let's take the second one now. B minus c. Again, this is going to be 3i plus 6j plus 7k added to minus 2i plus 3j minus 2k. So this is going to give us 3i plus 6j plus 7k minus 2i. So this is subtraction. So minus times minus, that is plus 2i minus 3j and then plus 2k. So eventually this is going to give us I plus the I is going to give us 5I. Then j with the j is going to give us plus 3j. And then 7k plus 2k is going to give us 9k. So this is b minus c. Let's take the last one now. The last one says 2b plus 3c. So 2b plus 3c, this is going to give us 2 into 3i plus 6j plus 7k minus plus 3c. That's 3 into c. C is minus 2i plus 3j minus 2k. So this is going to give us 2 times 3, 6i, 2 times this, 12j, and 2 times this, 14k. 3 times this, minus 6i, 3 times this, plus 9j, and 3 times this, minus 6k. So if you add this, and this is going to give us 6i minus 6i, that will go, no I again. 12j plus 9j, that will give us 21j. And then 14k minus 6k, that's going to give us plus 8k. So that's that about the addition and subtraction. Very, very simple that we basically don't need other examples to understand this.